Okay, so we've got about one or two things to say briefly on the end of chapter one before we move into chapter two. But the bulk of the time today will be spent with acids and bases. We will define them. We will discuss how we measure acid strength. And then we will start discussing structural factors that help us determine relative acid strength. So, where we left off with chapter one, we showed you electrostatic potential maps. We showed you polar bonds and how to indicate polar bonds. And one of those methods is shown here with the partial charges. The other one, of course, involves the vectors. Looking at this figure here on the screen, please tell me, is it possible to have molecules that have polar bonds but themselves are not polar? It is possible, okay? How? Who would like to tell us how it's possible? Yes, please. Okay, so the dipoles are vectors, so they have direction in three-dimensional space. And if those vectors cancel each other out, then the molecule would be nonpolar, even though it has polar bonds. And we have an example of that here with carbon dioxide. Water, of course, is polar. The dipoles actually reinforce each other in water. So we won't go over these examples individually here, but you see this figure has several examples of molecules with polar bonds, some of which are polar themselves, either having one polar bond or having polar bonds that reinforce each other. A couple of them which have dipoles that cancel each other out and are nonpolar themselves. So we need to distinguish between polar bonds and polar molecules. That's an important distinction to make. Okay. So to summarize what we've learned in chapter one and to summarize skills that you should have based on what we've learned in chapter one, we talked about skeletal structures. And if you are given a skeletal structure, you need to be able to add lone pairs to any place where the lone pairs should be. So that would make that into a Lewis structure. You should be able to determine the hybridization and the geometry of each atom that is not a hydrogen. That's something we talked about last time. You should be able to identify all polar bonds. Really, that's any bond that's not a carbon-carbon or a carbon-hydrogen bond if it's an organic compound. Then you should be able to compare bond lengths and bond strengths between carbon-carbon bonds or between carbon-hydrogen bonds. That's something we did on Wednesday in class. And then you should be able to recognize if it's possible to draw resonance structures. And if so, then actually draw those resonance structures. So there are homework problems that test your ability to do these things. So I would encourage you to practice those homework problems. If you want an extra challenging one, this is one of my favorite molecules, vancomycin. Vancomycin is an antibiotic. Some of you may have heard of it. We'll talk more about its chemistry and its properties in chapter 3 because it's relevant to some of the discussions we'll have and topics in chapter 3. Vancomycin was the subject of my PhD dissertation that I did many years ago. I was part of a team of graduate students that synthesized this molecule in a lab. But you can look at vancomycin, even a molecule this big, and you should be able to do these 5 things. Okay, so if you'd like a challenge for the weekend, then that would be a good one to take on. Okay, so before we jump into chapter 2, are there any final questions on chapter 3, chapter 1 topics? I'm all excited to get into chapter 3 and talk about vancomycin, but chapter 1 topics, are there any questions on those? Okay, well, let's switch gears now and start discussing acids and bases. We do have a question in the back now. Okay. Add lone pairs. Okay, that's our abbreviation for lone pairs. All right. So acids and bases, You've learned about them before in general chemistry. They should be fairly familiar to you. We're going to look at them a little bit differently, probably, in organic chemistry than you did in general chemistry. We're not going to be calculating the pH of a buffer solution or using equations. We're going to approach acids and bases in a more qualitative fashion. The main skill we're going to learn in this chapter is being able to compare acids or compare bases and decide which one is a stronger acid or base than another. Okay? First, we need to know what they are. We need to understand the definitions. And there are different ways of defining acids and bases. We'll start out in this chapter with the Bronsted-Lowry definitions. Okay? So, in the Bronsted-Lowry theory of acids and bases, what is an acid? Who can tell us? Yes, please. Okay, very good. An acid is a proton donor. So, of course, it has to have a proton. Basically, all organic compounds have protons, so that's not a problem. What is a Bronsted-Lowry base? Who would like to define that? Yes, in the middle there. Yes, a Bronsted-Lowry base is a proton acceptor. Okay. So, obviously, we know that to donate a proton, it has to have a proton. What structural features of a base would allow it to accept a proton? Yes. Yes, lone pairs. So you would have a lone pair that can accept a proton. Pi bond, the electrons in a pi bond, we know that pi bonds are weaker than sigma bonds. And so the electrons in pi bonds are more loosely held than the electrons in sigma bonds. So they can also accept protons. So we have, let's go to our first figure from chapter 2. And we will see that we have a list or a chart that shows Bronsted-Lowry acids and bases, many of which would be familiar to you from general chemistry. And the things we've talked about are shown here. All Bronsted-Lowry acids contain a proton. All bases contain either a lone pair or a pi bond. Charge is another way that we can identify these species. The acids will usually be neutral or positively charged. HSO4 minus is really one of the only ones I can think of that's negatively charged. And then you can identify the bases by either a negative charge or being neutral. Okay? So, and also note that some species can be both. We have water, which is a Bronsted-Lowry acid, and also a Bronsted-Lowry base. Okay? So, acids and bases undergo acid-base reactions. And let's take a look at just a generic Bronsted-Lowry acid-base reaction. HA is our generic form of writing a Bronsted-Lowry acid. And then B with a lone pair is how we would write a Bronsted-Lowry base. Some of them don't have lone pairs, but since most of them do, we will write them generically in this particular fashion. So here's our acid, here's our base. Acid-base reactions are equilibria, so we're going to use equilibrium arrows in this case. And we're going to use curved arrows to show the movement of electrons in an acid-base reaction. So the lone pair on our base is going to deprotonate the proton off of our acid. That's going to cause the sigma bond between H and A to break, and the electrons will flow towards A. And so what we're going to end up with is A minus right? Which is a grade that some of you will probably earn in the class. But in this case, it also has a name. What do we refer to A minus as? That is the conjugate base. Okay. And then BH plus, what do we refer to that as? That is our conjugate acid, exactly. Okay. So acid-base reactions, as I mentioned, they are equilibrium reactions. And whether they are favorable or not depends upon the relative acidities or the relative acid strengths of the acid and the conjugate acid. So an acid-base reaction will be favorable if it goes in the direction of the weaker acid. So if our conjugate acid is a weaker acid than the acid we started with, the reaction will be favorable. Okay? Conversely, if the conjugate acid is a stronger acid than our original acid, it will be unfavorable, and we will have more of our reactants at equilibrium than of our products. Okay? So to illustrate this with a specific example, let's look at some acids and bases that you'll be familiar with. HCl, every general chemistry student recognizes that. H2O, we know that it can be an acid or a base. In this case, we'll use it as an acid. H2O is going to deprotonate HCl. Okay. So acid, base. What is chloride in this case? It's our conjugate base, right? And then we have hydronium ion, or H3O plus, and that is our conjugate acid. This particular acid-base equilibrium is favorable, so that tells us that H3O plus must be a weaker acid than HCl. Okay, and we'll look at that in more depth in a moment, but indeed that is the case. So in equilibrium, we would have more of the products than the reactants. So if we wanted to, we don't have to, but if we wanted to, we could adjust the size of our equilibrium arrows to indicate that indeed this reaction is favorable. Okay? So in order to determine that an acid-base reaction is favorable or not, we need to have a way of measuring the strength of an acid. Okay? So one way we could do that, we could look at Ka. Okay, what is Ka? Yes, please. Yeah, Ka is the equilibrium constant for an acid-base reaction. So it would be the equilibrium constant for either our general reaction we've drawn here or our specific one right here. Concentration of products divided by concentration of reactants. Okay? So for a favorable acid-base reaction, what kind of a value would we have for Ka? Greater than 1 or less than 1? Greater than 1, okay? So we'd have a value greater than 1 because we'd have more products than reactants at equilibrium. If we had an unfavorable acid-base reaction, meaning we had a weak acid, what would the value of Ka be? Less than 1, exactly. Okay? Excuse me. So we could use Ka. However, the problem we face with using Ka as a measure of acid strength is that in organic chemistry, most of our acids are weak acids. And so the Ka is going to be a really small number. So acetic acid and citric acid, these are both weak acids. And these small numbers are not as convenient to work with. So to have numbers that are more convenient, instead of using Ka, we use pKa. What is pKa? Who can tell us what that refers to? Yes, please. Negative log of the Ka, exactly. Okay. So it's the negative log of the equilibrium constant for the acid-base reaction. Okay. So let's say we had an acid-base reaction with a weak acid as our acid, and our Ka, let's say Ka is 10 to the minus fifth. What would our pKa be? 5, exactly. I told you we do very little math in this class. This is probably the extent of the math that we're going to do. Okay? So, and acetic acid is pretty close to this. Acetic acid's pKa is roughly 5. Okay? So, because most of our organic acids are weak, then it is more convenient for us to use the pKa scale in comparing relative acid strengths. So on the pKa scale, would a stronger acid have a larger or a smaller pKa value? Smaller, exactly. So stronger acids are going to have smaller or lower pKa values. Weaker acids will have larger pKa values. So here we have a pKa table from our textbook. And we see HCl up here at the top. A negative pKa, that's telling us that the acid-base reaction, usually of that with water, that's kind of the standard, is going to be very favorable. And then all these others have positive pKa's indicating that they are weaker acids. Okay? So a couple things we can see from a table such as this. They're all organized in the same fashion, at least all the ones I've seen. They usually have the acids in a column on the left. And as you go down the table, the acids are going to be weaker. So the strongest acid in this table is HCl. The weakest acid is CH4 or methane. And so because of that, those pKa values are going to increase as we go down. All pKa tables I've looked at also show the conjugate bases of the acids in question. So you remove the acidic proton, and what you're left with is the conjugate base. And the conjugate bases are listed in order of increasing basicity as we go down. So the strongest base in this table is right here, the methyl anion, or CH3 minus, and the weakest base is chloride, Cl minus. Okay? And so we see an inverse relationship between the acidity of an acid and the basicity of its conjugate base. Strong acids have weak conjugate bases. Weak acids have strong conjugate bases. Okay? So we can see that from this particular table. Please don't memorize the numbers in the tables. The actual values of the numbers are not very important, and in fact, they differ. Different books will calculate the pKa values in slightly different fashions, and you'll see differences in numbers. But the ordering of the acids and conjugate bases that you see won't change. And so it's just the ordering or the relative acidity or the relative basicity that we are concerned with in this class. So, but one more thing that's important to note when we're talking about pKa is the fact that it is a logarithmic scale. Okay? So because it is a logarithmic scale, if we had two acids and their acid strengths differed by 1 pKa unit, what would be the difference in acid strength? An order of magnitude or a factor of 10, exactly. So this is like the Richter scale. If you've ever lived somewhere where they have earthquakes, you're familiar with the Richter scale, right? And an earthquake of a 7 is 10 times as strong as an earthquake of 6. Huge difference between those. It doesn't sound very big of a difference, but there's a massive difference between those two types of earthquakes. So same thing with relative acid strength. If we have a difference of 1 pKa unit, that's going to be a factor of 10 or an order of magnitude. We see here hydrogen and ammonia, both of which are quite weak acids, have a difference of 3 pKa units. So what's the difference there in relative acid strength? It's 1,000, exactly. So it's important to be able to translate those differences in pKa units into actual differences, and we can do that by remembering that this is a logarithmic scale. Okay? All right. So let's look at another pKa table. This is one from a different textbook. It's a bigger pKa table. It actually has 2 more pages. You see it says continued here in the corner. So this is just 1 page of the pKa table. But we'll look at this more detailed pKa table and look at a couple of things. So first thing we'll look at is we said that an acid-base equilibrium will be favorable if we are forming a weaker acid. So if our conjugate acid is weaker than the acid we started with. I drew one for you on the board and I told you it was favorable. So let's see if it is. We have HCl. HCl shows up right here. And what's right below HCl in this table? H3O plus. So we know that H3O plus is a weaker acid than HCl. Differ by about a factor of 2. So we're talking about 100 times weaker, essentially. So indeed, this would be a favorable acid-base reaction. So we need to define strong acids and strong bases. And so in this class, we will define a strong acid as one that has an acidity comparable to that of H3O plus or stronger. Another way to look at it is the pKa of a strong acid will be comparable to that of hydronium or lower. Okay, so we see hydronium here in our table, minus 1.7. Most chemists would say that nitric acid, which is only 0.3 pKa units different, is very comparable to hydronium. So most chemists would say nitric acid is also a strong acid. And so they'd say everything here from nitric acid to the top is going to be a strong acid. Everything below that is going to be a weak acid. And you see that our strong acids have negative pKa values. Our weak acids have positive pKa values. Okay? So that's how we would define strong acids. Any questions? What about strong bases? We don't actually see any strong bases in this table because this is just page 1 of our table. And none of these acids is weak enough for its conjugate base to be a strong base. Okay? But let's say you were back in general chemistry. You would have taken a general chemistry lab. If you heard the term strong base, what specific base or bases would you think of? NaOH, okay? So sodium hydroxide, or more generally speaking, hydroxide. The counterion, the cation is mainly just a spectator. So hydroxide is the prototypical strong base. That's the strong base that you would think of. And indeed, in organic chemistry, hydroxide is a strong base. And so we'll say that any base that has a basicity comparable to that of hydroxide or stronger than hydroxide is going to be a strong base. So we've got to go to page 2 of this particular pKa table. And we see water down here, 15.7. Conjugate base of water, hydroxide. So anything below hydroxide in this table would be a strong base. In this particular case, you see 2-methylpropanol, this compound, and methanol, both very close to water, 0.5 pKa units or less. And so we would consider those to be strong bases as well. So anything in the neighborhood of OH which would be CH3O minus down, we would consider strong bases. And there's a third page to this table. And so all of these bases here are going to be strong bases as well. Here's the methyl anion. That was our strongest base in the pKa table from the book. And then we have the ethyl anion, which is very, very similar. Okay. Once you get down here, in terms of base strength, there's not a whole lot of difference. They're super strong bases. Okay. All right. So any questions on identifying acids or bases in our pKa tables? Yes, please. We would probably consider that a weak acid because that would be more than an order of magnitude weaker than H3O plus. So H3O plus is what, like minus 1.7. So if you're getting down to higher than minus 1 or so, we would consider that, or anything around 0. Those would be considered weak acids in this class. Yes. Go ahead. It could be, because you can have more than one. You could have a proton in a molecule that's acidic, and you could also have a lone pair in that molecule that would be basic. So indeed, you can have something that would be both a strong acid and a weak base. You can have water, which is both a weak acid and a weak base. Most of these ones in the table here are fairly simple compounds. Other than water, most of them we're going to think of as either an acid or a base. But we will look at more complicated structures from time to time as well. All right, so let's go back to that page here. So we know that I've told you that if the conjugate acid is weaker than the acid, then an acid-base reaction will be favorable. And the conjugate acid and the weaker acid is going to appear below the acid in our pKa table. So another way we could look at it is to say that the transfer of a proton from an acid to any conjugate base that appears below it in a pKa table will be favorable. We have HCl here. Water is one row below it in the pKa table, so we know that's going to be a favorable proton transfer. We could transfer the proton from HCl to fluoride, and that would be favorable. We could transfer it to this nitrogen on pyridine, and that would be favorable. Okay, so proton transfers from an acid to a conjugate base that appears below it in the pKa table will be favorable. Any questions? Okay, then let's get our eye clickers out and practice this. So we have here a base. This is a base right here. It has its lone pair. And we have 4 acids listed. And then we have a part of a pKa table. And the question is asking you, which of the following acids can be mostly deprotonated, meaning have a favorable acid-base reaction with this particular base? Okay? So you can use this pKa table as a guide. You can talk to your neighbors and answer this question. It's a pretty quiet discussion I'm hearing out there. All right, let's try to get our final answers in the next 10 or 15 seconds here. Okay, any more answers coming in? We're up to 22. Going once, going twice. All right, that looks like all we have. Okay, so which one of these acids is mostly deprotonated by this base? Which one is it? Yes. C, okay. Would you like to tell us why you chose C? Okay, good. Mm-hmm. Okay. Okay, that was a very good way of solving the problem, right? One thing you'll find about acid-base problems is there's typically more than one route to getting the right answer, but the one you chose, in my opinion, is probably the most direct one. So what you did was you recognized that the pKa table here was just showing acids, and so you needed to convert this into its conjugate acid in order to make a pKa comparison. So to do so, you protonated the nitrogen, and that gave you something that looks like what's right here. And so you said, okay, the pKa of the conjugate acid here was going to be 11. And so I need an acid with a pKa less than 11 in order to have a favorable acid-base reaction. And there was only one of the choices here that fit that category exactly. So excellent, excellent problem solving. You'll notice that B didn't even appear in the table. That may or may not have caused some challenges or anxiety for you, but once you recognize where this conjugate acid appears in the table, you can identify the answer even though you don't see that one. The pKa of methanol is pretty close to 16. It's between 15 and 16. So if it had been in the table, it would have been in between these two. Okay? Any questions on how we solve this problem? Okay, so convert the base to the conjugate acid, compare the pKa's, identify the acid that has a smaller pKa than the conjugate acid of this base. Okay? All right. So now we need to discuss structural factors that determine the strength of acids. Okay? We can look in a pKa table and we can compare acid strengths in a pKa table, but that doesn't tell us why one acid is stronger than another. It's much more powerful to be able to understand and explain why one acid is stronger than another, why acetic acid is a stronger acid than an ammonium ion, for example. That may seem counterintuitive because you have a positive charge here and this one is neutral, but indeed this is accurate. So the book gives us 4 factors that can help us determine the relative strengths of acids. Okay? We have element effects, and element effects are referring to the atom that is bonded to the acidic proton in our molecule. So if we compare the identities of the atoms that bear that acidic proton, sometimes that can help us decide which acid is stronger than another. Okay? Inductive effects refers to atoms in a molecule that are not bonded to our acidic proton, but are instead somewhere else in the molecule. Those atoms can also exert an impact on the acidity of a compound or an acid. Okay? And we have resonance effects. As you might imagine, that has to do with our ability to draw resonance structures. And then we have hybridization effects, which has to do with the hybridization of the atom that is bonded to our acidic hydrogen. Okay? So, but before we go into these factors, there's a very, very important principle that we need to learn. And that is any structural feature in a molecule that stabilizes, by stabilize, we mean lowers the energy of the conjugate base, increases the acidity of our acid. Okay? We can understand this by looking at our generic acid-base equilibrium and remembering what we learned about equilibrium from general chemistry. The conjugate base is the product of this acid-base reaction. And if we are comparing two acids, and one has a more stable conjugate base than the other, based on what we know of equilibrium, that means more of that more stable product would form, right? Because the way equilibria work is we convert higher energy species into lower energy species, okay? So if we can make our conjugate base more stable, then that would increase the acidity of that specific acid. Or if we're comparing two different acids, the one that has the more stable conjugate base would be the stronger acid, because more of that conjugate base would form at equilibrium. Okay, any questions? So it's very important when we are considering these four effects that we are comparing conjugate bases rather than the acids themselves. Okay? So when we're going to compare two or more acids and trying to determine which one's a stronger acid, we're always going to be looking at the conjugate bases and not the acids themselves. Okay? So let's go on. Let's discuss the element effects now. How the properties of the atom bonded to the acidic hydrogen will impact the relative acid strength. And first, we'll go across the periodic table. Row 2, our most common row. We'll look at hydrogens attached to a carbon, hydrogens attached to a nitrogen, hydrogens attached to an oxygen. All right, and these empty valences could be anything. They could be other hydrogens, they could be carbons. It doesn't really matter. But then when we get to fluorine, of course, there's only one compound that has fluorine attached to hydrogen, and that's HF. So let's look at these pKa's of these types of species, right? So there's not just one compound that has hydrogen attached to carbon. There's a whole bunch of them. But if we look at methane, ethane, these sorts of species, their pKa's, depending on the book you use, are going to be in the 50 range, okay? A very big number. And then if we look at compounds with NH, ammonia would be a great example. pKa in the upper 30s, pretty close to 38, okay? OH, that could be water or alcohols such as methanol or ethanol. pKa right around 16. And then with HF, pKa is 3.2, okay? So is our acid strength increasing or decreasing as we go left to right across the periodic table? It is increasing. Why? Who can raise their hand and tell us why? Yes, please. It does have to do with electronegativity, okay? Okay, so we want to make sure we're comparing the conjugate bases, okay? So to make sure we have this comparison, we're doing it in the best way. Let's look at the conjugate bases. Let's compare the conjugate base of water, right? That'll be hydroxide. We'll go ahead and draw it out, okay? And we'll compare that to fluoride, okay? So you're telling me fluorine is more electronegative than oxygen, and that's going to be the key in understanding the differences between these two conjugate bases, right? So which of those two conjugate bases is more stable or lower in energy? Fluoride is, okay? And why? Okay, I think they all have the octet, so that's something they have in common with each other. Okay, yes, so fluorine is more electronegative than oxygen. What that means is that it is pulling on the electrons more tightly. So if you have a stronger attraction between the electrons in fluorine than you do, between the electrons in the nucleus in fluorine than you do in oxygen, you're going to have a more stable conjugate base. Okay, so you're having a negative charge, and we learned this in resonance in chapter 1. We learned that if you have the negative charge on a more electronegative atom, that's a more stable resonance structure. So it's the same thing with conjugate bases. Fluoride is more stable than hydroxide because that negative charge is on a more electronegative atom, meaning that the nucleus of that more electronegative atom is attracting those electrons more strongly. Okay? So fluoride is lower in energy than hydroxide. That makes the acid-base reaction of HF more favorable than the acid-base reaction of water. And we see that reflected in these numbers right here. We see about a 10 to the 13th difference in relative acid strength. Okay? And we see that the element effect is huge. We see very large differences in numbers as we go from left to right across the periodic table. Any questions? All right, let's go down the periodic table, right? We can compare elements in the same row of the periodic table. Let's compare elements in the same column of the periodic table. Make sure I get the values here. So we'll do the halogens, HF, HCl, HBr, HI. We already know the pKa of HF, 3.2. Chloride, the table I used to make these notes, it was -7. HBr -9, HI -10. So what's the strongest acid of our HX acids? HI. Does this correlate with electronegativity? No, it's the opposite. The most electronegative one is fluoride, but that's the weakest acid of all of the HX acids. So what property of the conjugate bases in these HX acids is responsible for this trend? Okay, Minnie? Size is key in this case, all right? So let's compare fluoride to iodide, all right? Which of those ions is larger? Iodide is larger, much larger, okay? So both of them have a -1 charge. So which of those anions has that charge spread out over a larger area? Iodide, okay? So when you're comparing two elements from the same column, it's not the electronegativity that makes the biggest difference. It is the size, because the larger anions can spread out that negative charge over a larger area, and that is more stable than having that negative charge confined to a smaller area, okay? So the element effect, when you're looking at two elements in the same row, you're going to be comparing electronegativity. When you're looking at two elements in the same column, you're going to be comparing size. Any questions? Yes, please. Yes, the relative stability of the conjugate base, exactly. Okay, so one last thing I'll tell you about the element effect. The book tells you that the element effect is the most important, meaning that the element effect has a more dramatic impact on relative acid strength than any of these other three. That is inaccurate. Okay? It is not true. I'll show you on Monday examples where the resonance effect and hybridization effect can overwhelm the element effect. Okay? So don't believe that. We do have an excellent textbook. I don't want to denigrate it. It's my favorite textbook for organic chemistry, but it's not infallible. Okay? What they meant to say, and what we'll say on Monday, is the inductive effect is smaller than the other three. That's what they should have said. But anyway, we'll clarify that more on Monday. and make sure you enjoy your weekend in a safe fashion. Stay healthy.